When we started to talk about confidence intervals, I didn't tell you the full story. There's a little twist that we need to add, and it's related to a man who went by the pseudonym, a student of statistics. And there was a man named William Seeley Gossett who worked at the Guinness Brewery, was a mathematician. This is in the late 1800s. And he was doing quality control and thinking about how well does a small sample reflect what's going on in the population. Now, we've seen that when we make a confidence interval, we take our statistic and then we put a fudge factor or some uncertainty around it by going plus or minus some sort of multiplier. We use the number 2 times the standard error. Now, this number 2 we've used as an approximation of 1.96. 1.96 comes from, of course, the idea that in a normal distribution, 95% of points will be 1.96 standard deviations from the mean. Now, when Gossett was working at Guinness Brewery, he realized that when you take small samples, the 1.96 was too small of a multiplier. And he literally cut up tiny pieces of paper, would put them in his hat, would reach into his hat, pull out the samples, and calculate and do this whole process of repeatedly sampling over and over and over. What happens when you have a small sample is that you don't really get a good estimate of what's going on. There's more noise, and you need to use a larger multiplier to truly have 95% confidence. So the take-home point of this is as your sample size decreases, if you have a smaller n, you need to use a larger multiplier for your CI. The great thing about this now is that the computer or statistical software will always choose the correct multiplier for us, but it's worth knowing the full story of how this works. So Gossett came up with this, what he called the T distributions. So instead of a normal distribution, remember a normal distribution, we specify with a mean and a standard deviation, and we use the letter Z when we talk about normal distributions. When we talk about T distributions, they're referenced in terms of your sample size. So as your sample size gets smaller, the distribution changes. As your sample size gets larger, it gets closer and closer to what looks like a normal distribution. Gossett wanted to publish these, but Arthur Guinness said, we can't publish anything that's related to brewing. So he published them under the pseudonym, a student of statistics. And you may have heard of these. These are why we call them students' t-tests, which we will get into in the next couple of weeks. So what these t distributions look like is kind of like a normal distribution, but you smush the top of it, and so more of the distribution goes into the tails. So if you look at this figure, you see this top curve here is a normal distribution, and it's when you have a very large sample size. This largest sample size I can think of would be infinity. And when it's infinity, the normal distribution and the t distribution are the same. But as the sample size is smaller, you get more of the distribution in the tails. So this dotted line that you see here is the t distribution for when your sample size equals 10. I know this is a little bit confusing, but the main point here is that if you have a t distribution, if you have a small sample size, and you try to use that multiplier 1.96 because you think you're going to get 5% in the tails, and you think you're going to have 95% confidence. So you can say, we are 95% confident that the truth is somewhere in between x bar plus or minus 1.96 times SEM. When your sample size is small, and we'll decide what that is, 15. If you use 1.96, you don't actually have 5% in the tails. You don't actually have 95% confident. In this case, you would be 92.6% confident. Now, what does this really mean? It just means that when you have a smaller sample size, you need to use the correct multiplier, which might not be 1.96. It might be something a little bit bigger, so that you truly get that 5% in the tails. So if we go back to the Frisbee example, let's say we wanted to estimate how much, I almost said beer, how much liquid can fit in the average Frisbee. We took our mean, which was 56.5. We took our standard deviation, and we made a confidence interval that used 1.96 as the multiplier. And here was our CI. So we are 95% confident that the true Frisbee, the average Frisbee, the population of Frisbee holds between this and this. But now we know that that is going to be a little bit of false precision, that this multiplier, 1.96, is too small because our sample size is not that big. It's less than infinity, n equals 10. What we need to do is use the t-distribution. We'll use a different multiplier, and the CI will end up being a little bit wider. But let's see what that means in practice. Write this down, 55.3, 57.7. And we'll see how that changes. Now, when we think about confidence intervals, remember this. A confidence interval, a statistic, is a rambling, bubbling, a manifestation of all of the potential results that could come out of that study. So we want to think about, if you had done this thousands and thousands of times, 95% of them would include the mean. That's the truth. Now, what we did is we did a study one time. And now that we know a little bit about randomness, that's equivalent to taking a random sample and saying, what's the chance that my random thing includes the CI? Well, it's this, right? So remember that the confidence interval doesn't talk about where the population parameter is. It talks about whether our CI caught it or not. This is a common mistake. It's not correct to talk about the probability of where that population mean is, because it just is. It exists. It's a number. We could get it if we got a if we got a census of every single Frisbee that exists, that there'd be no Frisbees left for anybody else. And once you get 100, 1,000 Frisbees, you know what the truth is probably likely to be. So we have to be careful that our CIs do not talk about the probability of the parameter. That instead they say there's a 95% probability that we caught it. Again, it's subtle, but it's important. All right, let's go back to student. So student, and you can look these tables up in any statistical textbook, or you can Google students' T tables. He said that when your sample size is 10, you need to use what's called the degrees of freedom, the DF, in order to choose the correct T statistic. So degrees of freedom is usually, in this case, it's n minus 1. Degrees of freedom is a complicated topic. We'll share a couple readings on it. You can generally think of it, it's roughly what your sample size is, or how much information you have in order to estimate something. In this case, with the degrees of freedom of 9, the T distribution we use should be a multiplier of 2.26. So it's bigger. It's bigger than what we would use in a normal distribution. That results in a CI, which is a little bit wider. Now, I think if you look what you wrote down, before it was 55.3 to 57.7. So it's gotten wider, but is it of any real world consequence? Probably not. But now we can say we have 95% confidence that we caught it.